Today we will be talking about the Lattice Boltzmann method. And this is a natural continuation of the last lecture from the last week, because last time we have been talking about FHP, about Lattice Gas Automata. And you remember I told you that there is a way to overcome the main difficulties with particle-based discrete cellular automata models, so lattice gas, and this is Lattice Boltzmann. And today I will be talking mainly about a little bit about the origin of the method, but mainly about the way it is working, the way it describes fluids, and the way you can basically implement it. I have only one lecture for that, so yeah, we have to squeeze in time. So let's move on. And I will cover two specific subjects. One of them is the basic Lattice Boltzmann, the most fundamental, the usual one. And then somewhere in the middle, I will switch into the LBMTau1 variant, which is a special kind of Lattice Boltzmann method prepared, especially in my mind. This second variant is very good for students. So this is the one you will be implementing during the labs, okay? So yeah, let's move on. And I hope that today the message will be covered. What is the message you will know in a second. So this is basically the reason we are working with Lattice Boltzmann is that it is very general. It can cover a lot of fluid flow phenomena. It is very fast, robust, and solves Navier-Stokes in many situations. And it's really easily accessible compared to other CFD methods. And it's a very good for the first step into CFD world. And as I know, all of you are there to learn basics and the fundamental methods. And I hope that you will, after today's lecture, you will understand how to get this done. Not maybe this, because this is a thermal Lattice Boltzmann. So, but I want to show you the scope of possibilities with it. There is an example of multi-phase flow with some temperature involved, so kind of boiling of the water. That's also possible. And all I show you here is very complex for standard CFD methods. If you wanted to do that with standard discretization of Navier-Stokes, you will be basically lost, especially in the second case where you have to track the free surface of that is splitting both phases. It is more general in Lattice Boltzmann. It's not two-dimensional model. It's three-dimensional. It can be three-dimensional without any problem. But let's move on. That's all about animations for now. Now we want to go into very much the grounds of the method, okay, itself. Where does it come from? In 1988, there was a paper from McNamara and Zanetti who are discussing the Lattice Gas Automata, okay, and they study hydrodynamics properties of the method. They propose to model lattice gas with Boltzmann equation. And what they claim is that this approach completely eliminates statistical noise that plagues the usual lattice gas simulations, and therefore permits simulations that demand much less computer time. So, because obviously, if you have a lattice gas automata, you may possibly get similar results like Lattice Boltzmann, but you would need it a lot larger and meshes, much longer computational time, and probably you would run out of the resources for that. It's similar like with molecular dynamics, yes? If we had this infinite computer, we would be able to make fluids. But anyway, so here so what is said in the paper is that they simulate for low Reynolds number less than 100. Today, Lattice Boltzmann can go really very high, but let's move on. So I will not discuss the letter itself because it's not easily accessible. I mean, it's possible to read and to study, but it's one of the pioneering work. Now it has 2,800 citations in physical review letters, quite a lot as for the physics. But anyway, what is the lecture goal? Because I have to really concentrate. My idea for this lecture is to give you complete introduction to LBM, so to Lattice Boltzmann, so that you can today sit down and write your own solver, okay? That's the main goal. And so that you can basically perform your own CFD simulation after today's lecture. And my assumption is you know nothing about LBM. So yeah, I want you to think it is simple, because in principle, the main method is very simple. Then the problems start when you want to implement specific boundary conditions, when you want to do turbulence, when you want to do some, and so on and so on. But this is up to you to study. Of course, I'm very happy to help. Many of them I did, but not all. And let's move on. So what we have in our zoo of the methods, yeah, as you remember, we started from the bottom, from molecular dynamics. You may start describing the fluids, or from the top, from Navier-Stokes, which is basically the macroscopic approach. Somewhere in the middle, I would say, is the Lattice Boltzmann method, which is called mesoscopic approach. Mesoscopic means neither particles nor the macroscopic equations. We will be working with completely different picture. We will be working with the so-called probability distribution function of velocity of particles in the domain. But let's see where does it come from. As you remember from the last week lecture, we worked with Lattice Gas Automata, okay? And oh, here is the pointer. And here we had those particles that were discrete on the grid. The grid was hexagonal, and the grid was a compound of many particles like this, with the main algorithm of two steps. One was transport, and the second was collision. And it was shown in the literature that with this simple method and approach, you may obtain solutions to Navier-Stokes equations, so all these vortex-Kalman streets. The problem was the statistical noise, which requires averaging and large lattices. But let's move on. The Lattice Boltzmann method is a kind of an approach that eliminates particles from the game. And now we don't have individual particles on the grid. Now we have the function, which will be described as a Boolean, which will have values from 0 to 1, not the values of 0 and 1, which was in the Lattice Gas Automata the case, but now we will have a function which has a continuous values from 0 to 1. So basically our grid will remain as it was in LGA. So it is the same. It has this, how many? It has a 0, which is resting, and 1, 2, 3, 4, 5, 6, 7, 8. So nine possible values of the velocities. Okay, the velocity is discretized into 9 values here. Okay, and but the values in each of these directions is from 0 to 1. So this probability distribution function is a function which describes the amount of particles that travel in a given place in the space into a given direction. This is the main concept, that in LBM we replace particles with the probability density function of velocity of particles having given velocity. This is actually a very known concept from statistical physics, where we have the picture in the different phase space. So we are not working with the, so we are basically describing the system in the phase space of position and velocity. And here is very similar. So our function will be a function of the position and time, and will describe these probabilities. Just to give you some motivation, so Lattice Boltzmann method is quite popular among years. It's a number of papers on Lattice Boltzmann is growing. And here I didn't really select all of them from the literature, because there are more specific journals where there are more papers based on Lattice Boltzmann. But what I did was just yesterday search for the number of papers in APS journals, from you know, the physical review letters, physical review E, and so on, and it's rapidly growing. Of course, there is like from 1995 there is a continuous growth, and I wouldn't say it's exploding, but the popularity of the method is quite large. So you may find many papers which basically use Lattice Boltzmann as an engine for CFD, for simulations of fluids, and not only fluids, because it's very like general. You can use it for different equations, also for quantum physics and so on. Okay, so what is the basic method we will be talking today? So we will cover the main ingredients of D2Q9 model. D2Q9 means basically this is two-dimensional. It has 9 velocity vectors. In the Lattice Boltzmann community, there are many different possible discretizations of velocity and space. You may discretize the space into 3-dimensional grid. You may use meshless grids. You may use different arrangements, but the basic one is the regular grid, which is basically 2-dimensional. So in 2-dimensional system, this D2 means 2 dimensions, and Q9 means 9 velocity components. And now we have to understand that there are those 2 discretizations, because this is the main difficulty in understanding Lattice Boltzmann in the beginning, because usually velocity and space discretization is coupled. Usually you have a velocity discretized in a given spots, and it has in a standard CFD, the velocity components are along the grid lines. Here is not. Those grids are decoupled. You have a 2-dimensional grid of space and 9-dimensional grid of velocity, okay? Which is basically another discretization. Our function can be understood as basically the probability distribution function. So there are 9 values from 0, which is a resting particle, to 8, okay? All of them are having different vectors of velocity associated, and you can see it as a histogram, okay? So all the statistical tools that you know can be used. For instance, you can compute the moments of this distribution. You can basically make many different things with that, and I will show you what to do to, for instance, get the density or the velocity from this distribution function. Because the main goal of the Lattice Boltzmann is to solve the transport equation of this function. So we will be transporting this function on the grid. And from this function, we will be able to compute Navier-Stokes equation. I mean, solutions to Navier-Stokes, which are basically velocities here, because we assume the density is constant. Okay. So the main character in the game is the distribution function. And now, believe me or not, but in the middle of this lecture, we will get rid of this main character. So it was introduced into not by the people who invented Lattice Boltzmann method, because the Boltzmann was actually working with this picture of the physical systems. It's a statistical description of the system by this distribution function, which is a continuous function on the has a continuous values on the in a given space and for a given velocity in a given time. So this is like we are looking on the picture in the phase space of velocities and positions. So you can basically draw trajectory through the solutions of the system. And yeah, so more like formal, it's a number of particles in finite element of momentum and position space. So you have a momentum position space, you know it from statistical physics. There is the this element of this size, okay, and it has the specific. So it can be understood as probability, okay, and this is for a given model of interactions, of course, for gas or fluids. Now, how to incorporate those interactions in Lattice Boltzmann? So first of all, what are the equations we are using? So for the probability distribution function, the main equation for the time evolution of this function is the Boltzmann equation. This equation is simpler than Navier-Stokes, so it can be directly solved on the grid later. I will show you. There are some assumptions about it, and there are books about the statistical physics of this equation. So sorry, but I will not discuss more. There are assumptions of molecular house in the fluid, so there is no velocity position correlation. So that's the ground assumption in this equation. And in microscale, 2-body collisions are solved. Okay, but this is exactly what we have in the FHP. Is like translation from the picture we had last time. Although in FHP we use 3-body collisions as well. But for the statistical approach, that's okay. We will not derive the equation, don't worry. And for the collision term, because this equation has the collision term. And a long time ago, long before the Lattice Boltzmann was introduced, 54, there was an approximation term for the collision, which is basically the linear convergence towards the equilibrium distribution. So this distribution of probabilities can tend towards equilibrium, as usually the physical systems are expected to do. And this equilibrium, if we know, then we can assume that our distribution will tend towards the equilibrium distribution somehow. Okay, let's not think what the equilibrium yet is. Then this travel towards equilibrium can be on different paths, okay? And the simplest one is the linear path. So we basically assume, again, assumption, that with a specific relaxation time, okay, with some specific frequency, there is a tendency of the system to go towards equilibrium, which is basically something we expect from any physical system, which is evolving naturally. And yeah, and this is how this Batangar-Gross-Krog term can be formed. Now, so that our function is going into equilibrium with this constant relaxation time. Okay, and where do we get the equilibrium from? So what we do in the Lattice Boltzmann, we are taking the Maxwell-Boltzmann distribution of gases. Okay, we take this distribution. It's amazing. It gives the fluid dynamics later on. And so this is standard from the statistical physics. And we put it into the equation of Batangar-Gross-Krog. This obviously may be found somehow different if you want to make another kind of interactions, not gas fluids, but some kind of different kind of interactions. Then you play with these collision terms. But this lecture will not cover it. We want to do fluids. So now I can understand you have many questions in your head now, which is okay. But let's move on into the implementation of it, of the Lattice Boltzmann, because for now, up to now, there was nothing non-very standard. Please have a look. We have the Boltzmann equation. We have the equilibrium term, so the relaxation towards equilibrium. And we have the Maxwell-Boltzmann distribution for gases, okay, where there are some velocities, temperature, and so on. Okay. With these ingredients, now we will talk about the discrete way of describing the system. Okay, that was the statistical physics. Now let's go from the discrete description. So now imagine that our function is discretized in space. The Fi are the discrete values of the density function, and we want to compute the density. The density is basically the first moment of the distribution function. So this is a sum of all the components of this distribution function. So basically you get a sum over from I equal to 0 to 8 or 1 to 9. It's up to us to decide what is the nomenclature. So it's simple. Yeah, this is the density, because I told you that the function can be interpreted as a number of particles that are traveling in a given space and at a given time. And if you sum them, then you get some kind of the density value. Yeah, you can basically scale it if you want, but this is the definition. With this definition, you can compute the main thing, so the velocity, because the velocity will be then just the density, I mean the density of particles traveling in a given direction multiplied by the primitive or the basic velocity vector. EI are the velocity vectors. So basically, if you take your grid, it can be 2 or 3 dimensional in 2D velocity vectors. So that will be in the code, but we have the 0 velocity. You have 1, 2, 3, 4, 4. These are the basic velocity vectors in velocity discretization. If this is 0, 1, 2, 3, 4, 5, 6, 7, 8, something like this. So all of these are vectors. And basically, if you want to use the momentum, so the density is equal to sum over all of them. And this is rho, sorry, not rho, but Fi times the EI, where EI vector, which is from this vector set. So you have 9 vectors around, okay? And so it's pretty simple. You basically take those two sums and you have your solution. So now you know everything almost, but you don't know the main equation. And that's a little bit of shortcut. I will be honest with you, because showing that this equation, okay, so basically the Boltzmann equation is a one-to-one to the Lattice Boltzmann method is a scientific challenge itself. So we will be using this equation. It's a kind of discretization of the previous one. It's a discretization of the Boltzmann transport equation in a regular grid. So we have this transport term where you have the density of the the probability density function in a point X in the grid plus, sorry for changing the letters, EI, which is there, is the same as CI, okay? So here I just use the CI. CI is the velocity vector pointing in the I direction, so 0, 1, 2, and so on. And so the value of the probability density function in a spot X plus CI, so what does it mean? You have a grid, okay, which is regular. You have a grid, it is regular. Okay, in a given spot in the grid, you want to calculate now the Fi value in the point X plus Ci. So for instance, let's say we are at the point, we are doing this for the direction I equal to 1, okay? I equal to 1 is this one. So Ci is basically, Ci is equal to Ei, okay, is equal to 1, 0. Is basically the vector pointing to the right. So now this equation says, okay, this equation says that F in the next time step, okay, in the direction of Ci, so basically the X component of Fi, so the component 1, in this spot, because C1 is directing towards this, okay, sorry. Okay, so that this in the next time step is equal to the collision term. So this is basically computed locally, because this we have to just compute the Maxwell-Boltzmann distribution, plus the value of Fi in our node. So basically you compute the next one, taking the values from the previous one, and you do it over the whole grid. So you basically compute here, here, there, 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 and there. And this is one step. So you do the transport step. This is collision step, and this is transport step. Now, if you remember from the previous lecture, the FHP model, Lattice Gas Automata, we did the same, but on the particle based. So we took all the particles, we transported them, and then we computed collisions, and then we transported collisions. Here, everything is embedded in this single equation. So we basically can now understand, hopefully, why this is so simple, because now you have to just solve this simple equation on the grid like this, and you have your CFD solution. And yeah, so let's see in details. So this is an example of transport of a density function on the grid like that, where all the components are marked as those triangles. So what does it mean that this triangle, for instance, is larger? That means probability of particles going upward is just larger. So basically more particles travel to the upward and so on. So now single time step of Lattice Boltzmann. And how does it look like? Have a look on the time time equal to 0. Of course, this all happens in one step. I will show you in several steps just for you to see what happens. In like 1/4, some of them goes this, this, this. This is the transport step of Lattice Boltzmann. But it is not that simple because I showed you only for this single component, for this single spot. This happens at once on all the entire grid. So, for instance, from this grid point, the probabilities go around, scatters towards neighboring nodes also in the one step, time step. Okay, so again, this would be the back step, but it does not happen. Our step looks like this, and this is the transport. Now, I will obviously show you how to do the simple implementation of this Lattice Boltzmann, but let's continue the simulation model. So the Lattice Boltzmann, it consists usually of two steps. They can be combined in the code or in the algorithm, but the main algorithm consists of collision and of the transport. The collision is just relaxation towards equilibrium, how to do this. So yeah, now I will talk in terms of the code because I like it. It is an approach that gives you the feeling that you can basically do it by yourself. And this is exactly what I want you to think after today, because it's possible. Lattice Boltzmann is really, will give you so the driven cavity you will get like this with Lattice Boltzmann. It's just, okay, so how the code would look like. And you can find thousands of Lattice Boltzmann implementations in the web. This is not a problem, but it's more about to understand. So the density function is actually very simple. It's a function that has 9 components in each of the grid points. So what that would mean? The data structure for this would need to be 9-dimensional table. So you have the table of, sorry, not 9-dimensional, 2-dimensional table of 9-dimensional values. So it's like 2 by 9, okay? So it's something like that. Why do I keep it twice? Because this is obviously not the only choice. You can do it in Python, in whatever. I just do it C++ because it's the simplest for me to think and to actually make it straightforward. So let's say these are float values. You can use doubles, no problem, but floats works as well. It is a density function. I keep twice. In a moment, I tell you why. It is, in my case, 2-dimensional with the equal x and y size, and I have 9 dimensions for the function. And I keep it twice because, as I told you, the scattering goes at once in the entire grid. So how to do it in place? You cannot. You have to use kind of ping pong. So we scatter to the copy, and then we exchange them. We scatter to the copy, and we exchange. This gives us a lot of freedom in parallelizing the code, for instance, because you don't care about the race conditions or anything like that. You can do it basically in parallel from one grid to another. So the scatter, because I don't know if this is that obvious, but from what I see in your faces, seems like not easy. But the thing is that if I do it in place, in one grid, then scattering of this value towards this value will ruin my code, because then scattering from this towards this would be not possible because I would override it. And you cannot do it one by one. You have to do it at once in the entire grid. This is what the cellular automata was about. You remember that we had the algorithm that works in the entire grid at once. And here it's the same. So basically the copy of the grid is saving our life because it's making it super simple. Now you scatter from 0 to 1 or from 1 to 0, 0 to 1, 1 to 0. It's a ping pong technique. Okay, and now the domain size is LL and the directions are 9. Okay, it should be moved, of course. Okay, now the algorithm. So let's move from the, I don't like to implement the main thing first. I like to prepare my ecosystem. So to prepare, we will first show the implementation of the main ingredients for actually analyzing the result. And this is computing density and momentum. For the density, I already told you, just sum the values of the function. So you basically want to compute rho, and rho is equal to rho plus density function in x plus y times L of I. Why do I use this x plus y times L? This is a technique to keep the two-dimensional table in one-dimensional table. Okay, that's only it. You can use two-dimensional, no problem. But then the table becomes 4 dimensions, and this. Anyway, it does not matter. Here in the main implementation, I have just used the mapping for the x, y. So, okay, what is c? C is not the velocity direction. This is the number of the grid from which I want to compute the density. Here, C is just 0 or 1. So this is the first or the second copy of my grid, and I is the velocity direction. So this now is super simple. Yes, that's just a sum. Any questions about it? No questions. Very good. Now the velocity. The momentum. To compute momentum, you basically take the sum of the probability density function and the velocity here, EI, the velocity directions. And for that, we have to use the density directions which are coded, kept in some way. And for this, I use one-dimensional table of velocity components EX and EY. So I have I will show you those tables. I just have all the velocity vectors like 1, 0, 0, 1, minus 1, 0, 0, minus 1, 1, minus 1, and so on. I keep them into tables in EX and EY. And these are here. Yeah. I didn't define them before, I'm sorry. But anyway, to compute rho, so for compute rho, we already know that we sum this density here. But for ux and uy, you separately compute you multiply the density function in a given space by the velocity. And you do it in a loop from 0 to 8. Yes, and this gives you this. I'm sorry for inconsistency on my slides, but I just noticed that now that here I have from 1 to 9, here I have from 0 to 9, because obviously this is for the scientists, this is for programmers, yeah, because with C++ we enumerate from 0 to 8 to 9, yeah. Okay, and then at the end, to get velocity, I divide by the density, yes, and I get the velocity vectors. Okay, if you have velocity vectors, you have your solution. So now let's move on to the main algorithm, which is the collision and transport. And now in Lattice Boltzmann, you may split those two into two steps. The collision step will be basically computing the collision term locally. So we want to compute the equilibrium distribution function first. So we will compute this FEQ from the Maxwell-Boltzmann distribution in the discrete form. And now again, we will be using a form of the distribution function known in the literature. You can find in many books, and the derivations are there as well. This is the discrete version of the Maxwell-Boltzmann distribution in Lattice Boltzmann language for the Lattice Boltzmann. I'm sorry, for our grid, where the velocity vectors on the grid are enumerated as Ci. These are the discrete velocity components, Ci, and you basically compute the equilibrium at a given direction. And this is computed from the density in a given space and the velocity. So to compute equilibrium distribution function, you have to compute the right-hand side of this equation. And for that, you need the velocity, the macroscopic velocity, and the density. This you already know how to compute from the previous slide. You also need to incorporate the velocity components on a grid, Ci, and Cs is just the lattice sound speed, which is basically the sum of the weights on the lattice and the Ci and the Ci. So these are the velocity directions. Believe me, everything which is on the right-hand side, you know. Okay, so this is given. It's not like implicit implementation. And where do we get the weights from? Yeah, you will get them from the literature. They come from the discretization on the grid. There are some specific rules of the discretization of the grid. You have to fulfill some constraints, and from these constraints you can derive weights. So for two-dimensional D2Q9 model, we know from the literature what the weights are. If you want to use another kind of discretization of the grid, you may have to compute them by yourself. But 99% of the people in Lattice Boltzmann community, they don't do that because they are given for a standard grids, okay? This, for instance, if you want to discretize the velocity space by yourself into different set of directions of the velocities, then you have to recompute weights and all this stuff which is there, yeah? But for the given velocity and time and the space discretization, you already know the components of this, I mean, these properties of the grid, yeah? And this is just the unit matrix I, which is there, yeah? And so to compute right-hand side, you have to translate this into the code, but for that you need those data. And data are in the literature. There is a very nice set of books in Lattice Boltzmann, of course. I can give you some references, and you can read more systematically the derivations and so on. The most, I think, useful book for you will be the book of Kruger. That's a book which systematically introduces many different Lattice Boltzmann models. But for D2Q9 is standard. For me, it's like, you know, in every community you have those ground models, and D2Q9 is like the basic in Lattice Boltzmann. And so everyone knows the weights are here. You just have the weight for the zero component of velocity. So the resting particles, this is 4/9. Then you have the x, I mean the right, up, down, and left, and these are 1/9. So this represents something, you know, you can understand something about the distance of particles. Yeah, therefore this is larger, and then you have 1/36 for the components which are 1, 1, 1 - 1, and so on. Yeah, and these are here. So you enumerate 0, 1, 2, 3, and so on up to 8. And then you have lattice vectors, here again as Ci, and this is the resting component. So 0, 0, this is right, up, left, down, yeah, and so on. So you have these components of the velocity on the grid. So the sound speed, you can compute from this equation, and you basically take it as 1/3, yeah, because if you do it, then you have... Sorry, here. Oh, I'm sorry. Very good. Okay, so let's compute together. So you have 1/9. Maybe I got something wrong here. You want me to compute it now? Or, I mean, yeah, I'm sorry. This should be 2. Yeah, might be my mistake. I mean, it's like if you do the the proper implementation, if you do it technically, if you implement, you don't care because these are the values from the literature. You take them and you use. So I may have it written wrong. I'm sorry. So I will check it for you. I don't. It should be here, yeah? 1/36, yes? Okay, right. Here, yeah, you're right. It should be, yeah. Okay, you're right. So 1/3. Yeah, so this is a mistake, but the value is okay, yes? Thank you. So that's how I probably prepared the slide. So I took this value I knew, I took the equation I knew, and then I put all of this together. So that's okay. Because I didn't compute those weights and those data. I will be honest, these are given, yeah? But okay, thank you for remark. Okay. Let's move on. Now to implement the equilibrium distribution function, you basically take your equation like this. You may rewrite it in different forms. This is more like standard one from books for the implementation, because if you take all this and just rewrite a little bit the algebra and you take the CS over is squared, then you get you get this, okay? And if you reformulate in this way, then we will implement in such a way that it's now I hope that it will be very simple for you, because that's the main actually difficulty is in implementation of this collision somehow. And then if you have this, it's super simple. So let's move through that. So the collision term, you do the loop over I, okay, in all the directions of the velocity space. And we calculate directly from this equation. So see, the W are the weights that we have somewhere in the code. Of course, keep them in the one-dimensional table. You have the density computed before. You have this 1 plus 3 plus EX. So we do this for separately for the X and Y, because you have to do this multiplication. So EX times UX plus EY times UI. And then you add 9 over 2, this is this, and so on. So you basically go on through all this equation. And this is it. You have equilibrium, okay? The equilibrium over the entire velocity space, because you do the equilibrium in a given point for all the velocity directions. You have to sum it. And then we will use this equilibrium and put it into this equation to compute the distribution with the equilibrium. I mean, we want to, no, this is not transport. This is the equation which tells you how the function in a given place changes when our system tends towards equilibrium. So we will put this into this equation. Technically, this is very simple. It's like one line of the code, yeah? So we do this. We basically take the new value of the density function in a given spot, this is that, is equal to the density function from the previous time step minus 1 over tau. Tau is a float number because this is basically the relaxation time, multiplied by df, so our value minus feq. I'm sorry for this, but this gives you more motivation to maybe read even. Okay, so basically this is our collision step, and that's it. This is collision step. That's the end of the story in this particular part of the algorithm. There is nothing more. Now we have to do the transport. And the transport of density function has to implement this phenomenon. So we have a function in a given spot, and in the next time step, it has to go around. And this is described by this equation. Now you see what we did. I could start from the theory, like we have the transport equation, we split it, do this and that, but I like from this side. I hope you like it. So now we split it, our equation, into the transport and collision term. Collision was done, and transport is here. Now this f with tilde here over the f function is basically the one that we computed from this step. Okay, so we compute the f tilde, and now we will do the transport of this f tilde around. So this is basically written in one equation. How to do that? So we go over all the, so here is written in different way, because I wrote also this double loop over all the spots in my grid. So we go over all spots in the grid. This can be parallelized easily. So Lattice Boltzmann is perfect for parallelization, because you don't care if you use this ping pong technique, then you parallelly do this in each of the spots. And we go over, so for each of the node in our grid, we go over all the lattice directions. Now, for each of these directions, we compute what is the position of the grid point in a given direction of velocity. So Ex, Ey, remember, these are the velocity components. Now, if we are at a given spot in the grid, so for instance here, we want to know what is the grid point for this direction of the velocity, because remember, velocity and the space discretizations are decoupled. I mean, they're somehow coupled, but they're different. Now, so from this velocity, we know that the grid point in this direction, and this is exactly what we computed here. XP and YP is the position of the grid point in a given lattice direction. So for this lattice direction, it will get this, yeah? For this lattice direction, we will get this. So now you see, having the direction, the grid point in a given direction, so XP and YP, I will not describe how I did it. This plus L and the modulo L means we will have the periodic boundary conditions. And then for this direction, we can directly compute this equation. This is so simple. You go from, so you compute the next, the new value of the density function in the, I mean, on the grid 1 minus C, why 1 minus C? Because we are doing ping pong. So for the C, we compute it from 1 minus C and so on. And then, so 1 minus C in the position XP plus YP for the direction I is equal to the value from our node. So basically, this is exactly what we wanted. This value of the density function is transported here. This value is transported here. This value is transported here. This value here, and so on. So that's the equation. And that's the implementation. Now, if you listen carefully, you have the whole lattice Boltzmann solver in your head. Because now we have the computation of density, of momentum, we have the collision term, and we have transport term. Okay, and this is a complete lattice Boltzmann solver. Obviously, there are more details if you want to go into more interesting systems. Just to give you a little bit of introduction to boundary conditions, you can use the very simple technique for boundary conditions. So for instance, if you have a wall, let's say this is a wall through which there is no flow, so there is a fluid going upwards, will be going downwards, so it's like collision with the wall. So on in terms of lattice gas automata, we would just reflect the particles. Here we reflect the density function from the wall. So all the populations, or populations was the missing word, all the populations of this density function that are going towards the wall will be reflected. And this will give us no slip condition, means the zero velocity along the wall. And it basically works like this. So we want to have something like that. So the populations that go along the wall will just go along the wall, but populations that are pointing towards the wall will be reflected. And this is the situation in the one time step, okay? And to implement that, you basically, okay. So to implement that, we need to mark our nodes in the position space. We say which nodes are the solid ones, so those from which the density function will be reflected. And for that, I use the additional flag table. And if I have this flag table, in the transport part, I just implement it in that way that I check if our flag is equal to 1. If this is equal to 1, that means there is the reflection of the density function from the directions which are towards the wall. So if there is, for instance, a wall here, let's say this one is a wall, okay, this one. Then what we need to do, so this is the situation when there is a 1. So let's say the particle population going from here towards the wall has to be reflected. Then we don't do the normal transport which is there. The one which is below is the normal one, this one. Okay, this is a normal transport, but we do a different way. So we basically apply that not the value in the I direction, but the value in the inverse I direction is equal to our value. That means, so let me draw it in larger because it's completely messy now. Where is the let me draw it again. So to make the reflection, let's say this is our wall, and so the population which goes in this direction will not be copied here as it would be in the usual transport in this node, but the inverse that, yeah? So basically, and this is exactly what is here. And the only thing that we need is the inverse table, which is basically mapping the direction to the inverse one. And that's all. That's so simple. And actually, this, I will claim that this is what you see here. I know it sounds like, oh, it's just a boundary condition. But this, what you see here, is the main reason the LBM became that popular. Because this super simplicity of boundary conditions, even though there are not that, there are some flaws here, there are some problems with the boundary conditions as well, as all the methods have its own problems. But these boundary conditions, the simplicity of this gave a lot of power to the solutions with this method, because it is so simple, it works, it's robust, it gives a pretty nice convergence of results in very complex phenomena, especially those porous medias that I'm working with, because you can basically just apply that, and with this flag which is there, you can do crazy stuff, which is really not accessible for standard CFD solvers that easily. Okay, now this is the complete LBM code, and it's a complete solver. Believe me or not, but this is so simple. You have two steps. One is the one in which you compute the density and the velocity. Now this is the full implementation which gives you the velocity, and this is basically the main method. It is computing the equilibrium, which is there. Okay, it's a little bit different, a little bit in details, because I use a bit different way of computing this, the density function in next, like lattice node, because I don't use tau, but I use omega. Omega is just 1 over tau. It's like, but don't worry, you could implement with the, from the previous slides without any problems. It would be the same, but I use omega instead of tau. I use it because I have like many of LBM implementations, and here I also want to show you the different approach, so that you don't get scared when you see different codes of different people. But anyway, it's the same. You see, there is this inverse, there is the IP, and JP is just the next lattice node, and so on. So you basically compute it, and what else here? And yeah, what else do you need to really compute it? So to compute the flow with the lattice Boltzmann, because these are just two functions, I didn't tell you. So you have to do two things. One is to do initialization of the probability density function. So the function df has to be first over this should be initialized. How to do it? From the solution the best, yeah? If you have the boundary conditions or some solution first, or you can start from the like zero and homogeneous distribution of density, you apply some boundary conditions, and this is the way you can start. You can use equilibrium to actually initialize your density function, and then you do this in loop, yeah? This is the computational loop. This gives you time-dependent solution, and so doing that, you can use U and V to visualize, to get your results, to get some cross sections of the results, and so on. Now let's move on. What this really gives you. So yeah. The full LBM code that I will be showing you some results is exactly what you've seen here. I also want to show you results of this particular code, and I mean this particular technique without any difference to this what I showed. So all this simple solver gives you, after implementing one little extension, because this is something I just love in the CFD world, this is the advection of particles. If you have your velocity solution on top of this without any interaction, so you can put massless particles. It's like putting markers in the flow, but those particles are showing the behavior of the fluid, really, because if you show the velocity distribution, this is not the solution. I mean, this is a solution, but this is not what you see in the nature. In the nature, you see particles that are traveling. Why is it important? Because if you have particles, they obviously go along velocity, yeah? But those particles will show you different paths than if you looked at the velocity vectors, okay? Because the particles are advected in the flow. They move along the so-called streak lines. And those streak lines are the most interesting because then you can really feel the fluid. Now let's see the LBM in action. So now I show you different implementations of LBM. This is one which is directly what you've seen just a second ago. So this is the solver that implements the basic LBM. There is no like turbulent model involved or anything like this. This is direct solution of Navier-Stokes with the code which is very similar to what you've seen just now in the slides. I hope this gives you motivation because this is periodic. Obviously, you see there is periodicity. There is, let's see again. There is periodicity. There are vortices in the flow. So you see all this phenomena that happens in the corners. There are particles traveling. They also go. They also go in periodic system. I mean periodically. One little ingredient that I didn't mention is the body force, because I use body force to accelerate the flow. So there is some kind of direction of the gravity that pushes the flow to go through, and so on. Okay, let's go. So that was the first to show. Also, I know that there are people working maybe with MATLAB. There was a website. I think it is not available anymore, so it's good that I took the snapshot at some point. Exolet.com. You might check it, I don't know, but they showed the full LBM implementation on one page, and they were just showing it. At the time, Lattice Boltzmann was not that popular, and I remember it was amazing that when I've seen that, wow, you can do kind of porous medium solution with this code. It's basically exactly the same. You just implement you see all the data, the reflection, and then you have the computational loop, which is just enrolled. You could even do it smaller because, you know, my code in C++ was smaller than this MATLAB. Yeah, and basically that's it. So, and you get the solution. There you have fluid going through. Yeah. There are some problems with this, of course, but I will not go into details now. Yeah, so now the picture I want you to remember after this lecture is that you can think of the standard Boltzmann equation as a way to introduce the transport and collision terms into the Lattice Boltzmann method. And now, just to be honest with you, these arrows are oversimplification of what I showed you, because there are papers showing that this is exactly the same as this. Okay, it's not that simple. Now let's move, because I want to cover more. And yeah, so again, simple phase flow, just to give you more and more motivation to work with that. There is again nothing more from the code that I showed you. This is my implementation, so I know what is inside. This is the transport of particles through a complex system of this narrow passages in the porous medium. What was not that simple was to advect those particles in a way that they actually go through the system, because it's the more complex it is, the more obstacles you have in the flow, the more difficult it is to numerically advect particles. So that was the challenge here. Let's move. And I used this for the tortuosity projects that I was working during my PhD. And yeah, that was the time I was using actually the single phase Lattice Boltzmann for that. And I also was playing with the computer games at some point. That is a very simple game in which you have the Lattice Boltzmann solution live in real time in the scenario like this. So the player has to mark the parts of the system which are not permeable, and the fluid goes around, and there are some ships that have to go to the white, not to the red. Don't ask me about the motivation for the mechanics of the game like that. The reason I show it is to show you the actually how fast the lattice Boltzmann is, because this is the real-time simulation which happens at the time the player is playing. There is a lot of applications like this in the web where people are playing with lattice Boltzmann live, and this is actually, it is not even GPU. This is actually the CPU on the NVIDIA shield. Which is pretty funny because NVIDIA was created to make GPU, or is it GPU? No, this is actually JavaScript implementation. It works that fast. But Lattice Boltzmann is not only 2D, it is 3D model. And here is a nice example of, I hope nice for you because it's mine. I was playing with Lattice Boltzmann in 3D as well, but I didn't implement 3D for this particular model, for this particular problem. It was 2012, I remember. And why do I remember? Because I won a competition of Palabos library. There was a library from the Geneva University, from Jonas Latt has organized this. This is an author, one of the authors, the main person behind Palabos library. Palabos is a very nice C++ implementation of Lattice Boltzmann, and they were playing with the idea that they want to, I mean, they wanted to show the library in a nice way. And they asked people to prepare a simulation with the library they have in a way that it shows off the Lattice Boltzmann capabilities. And I figured out that I can combine this with my computer graphics interest. And I took the solution from Palabos, and I took the solution of three-dimensional problem of splashing droplets. So I just created a special script for Palabos, which makes the droplet dropping into the water. But then I cut the solution and I put into POVRAY. POVRAY is the three-dimensional rendering software in which you can basically make the, basically in the POVRAY, you can basically make the rendering like that. And at some point I will show you this, okay? Still have some time, so let's move on. I have the animation for that, but later. I was also playing, and this is also my code. This is in compute shaders, so it's also real time, but it's quite large. It's full HD simulation of multiphase flow. There is a model, Shen-Chen model. Not only this one, there are more models, of course, but the Shen-Chen is the simplest one, in which you can do multiphase flow. And there is an example. Actually, this is something not many people did. I did it because I was playing again. It's my computer graphics interest that led me to do that, because people never, I didn't see anything like this before. Like, people didn't really play with the what happens in the exactly in the phases of the flow. What you see, the standard part is the division to two phases. One is this one, which is in between of these droplets, and the other are the droplets. So you see the phase transition. The system becomes, so the equilibrium is like one droplet, or the droplets which are separated, but there is some mass transport between droplets. They combine together. There is surface tension, which is basically not put by equation. This comes from the physics here. And yeah, so those droplets are joining together, like here, like plum should be there, like plum. Yeah, you see. But what interests me more is, and yeah, I think would be worth to even study the model like this, is what happens in between. There are some waves of mass that are transported from one droplet to another. And when they combine or split, these waves are generated. And these waves are like order of magnitude faster than what happens in the main flow. So you see the transport of how the physics between droplets is happening in one phase, so how the mass is transported. Because I basically amplified the colors in the density distribution function. So I just see the density in both phases on different levels. So colors are not representative for densities. Colors are the, yeah, colors are showing the transport. Now the turbulence modeling is also possible. So Lattice Boltzmann, you can basically, if you have large grids, the large enough grids, you can go higher and higher with Reynolds number. But there are also models which are mimicking turbulent effects by smoothing out the small scale effects. If you smooth them out, then you can compute the very high Reynolds numbers without limits on them. Because the problem is that if you increase Reynolds number, you are decreasing the size of the vortices. And if you go to the infinity, then you would have infinitively small vortices. I oversimplify the picture, but the problem with turbulence is that you would need to have infinite grids, really. Yeah, so but you can cheat a little bit and use, for instance, Smagorinsky model. And this was done at one of the conferences with my colleague, Nicolas Delbost, who had a very simple implementation of Smagorinsky, and just let me implement this to my GPU implementation with compute shaders. And this is exactly what happens live when I play with the code. Yeah, it's still two-dimensional, but yeah, it's pretty nice because you see all the effects are very dynamic, and you have all the effects you can put on and move the boundary. It's actually pretty interesting that it works that good. Now the moving boundaries are possible. So for instance, in the engineering world, people like to have boundaries that move, rotate, deform. So everything that, like, you have the windmill or something, simulations like that. And just an example, I was playing with that as well. That's my code, because I really liked to have it implemented, because doing that in the standard CFD is pretty much problematic. And that's just a paper in which the boundary conditions for the lattice Boltzmann are described in a way that you can have them moving. I'm not pretty sure. I was not studying this more. I just implemented what was in the paper. I don't know how much exact I am. Here I don't show you much of my scientific work where I was spending like months or doing exactly the computation. I'm just showing you the capabilities of Lattice Boltzmann. So don't rely on my solutions that much. I mean those, because for the moving boundary, I'm pretty much not convinced they are exact. Okay, but the Lattice Boltzmann method applications are very wide. People use it in many situations. One of them is a nice example of EXA.com. It is 2010 when EXA has announced that they use Lattice Boltzmann to compute the drag over the bobsleigh object in the sport, so to optimize, and they helped to achieve record-breaking performance for USA men, first gold in 62 years. Who knows how much CFD was used here, really, but they used it. So might be that, yeah, it's interesting to see, because they were actually computing where is the drag. So probably this is kind of drag, the most drag places. So you see this person who is sitting first has the the most influence. So probably maybe the optimization of the shape of the first person is like the most important in the drag reduction. Yeah. Okay. Now I will now move into the LBMTau1. We still have some, like, what? We started 8:15, so we have 15 minutes, yeah? And I think we can do it. It is now what I want to show you is the simpler approach towards Lattice Boltzmann. It's a bit crazy what I say, because basically Lattice Boltzmann is simple enough, one would say. And I encourage you, if you want, implement Lattice Boltzmann with these slides and with this what I showed you. You are able to do that. Maybe there are some ingredients you don't know, but this will solve during the labs, or you write to me an email. I will help you. You are welcome. The Lattice Boltzmann is the solution itself. It is half of our exercise. It's okay. But I will now try to encourage you to get familiar with the LBMTau1. Now, you remember what tau was. Tau was the relaxation time towards equilibrium. So this single value, what were the values of tau? So tau has some specific range of the values. You can vary tau, and by varying it, you are changing the properties of the fluid. So you basically change the viscosity of the flow. because one of the properties of the fluids is viscosity, and it is changing with the properties of the collision term. Now try to concentrate, because I will simplify your life very much. That's the main point now. So we have now, our needs are much bigger than what I showed. We want to compute flows in systems like that. So this is three-dimensional system, compound built of three-dimensional spheres, which are packed all together with some software. And by what we want to achieve is to efficiently compute the fluid flow through this very large and very dense system of obstacles. And to do that, you can use different techniques. This is done with Palabos, with the Lattice Boltzmann. And why did we use Lattice Boltzmann for that? Why didn't we use finite volume or another kind of discretization? Why didn't we use simple, like I showed you, the semi-implicit function? So the reason for that is that, as I told you, the collisions on the border between fluid and no-slip nodes, so all these obstacles that are here, are super simple in Lattice Boltzmann because they are local. I do this locally, just on the grid. To do that, for instance, in a software like OpenFOAM, the one that I want to introduce you during the labs, because you will be also working with that. It's just a software that you download and you create a grid, is that you have to create a grid. And to create a grid in such a system is super complicated. It's like the problem itself. There are people getting money for creating grids in CFD because there is no software, the state-of-the-art software that will discretize this into a grid which works in finite volume easily. You have to spend a lot of CPU hours on the grid itself. And Lattice Boltzmann does not need it because you basically compute it in the regular grid here in the between of the system. Okay, but now the problem with Lattice Boltzmann that emerges from that is that you remember how many dimensions we have for the function? In 2D, we have 9 directions. It can be more. It can be like 15, for instance. But in 3D, minimum to get Navier-Stokes, I think it's 15. So you have 15 dimensions for velocity for each grid point. So how much memory you need? You need a lot of memory to keep the density function. Okay, that's the problem. Now let's solve the problem. How to solve the problem? The problem is to get rid of distribution function. So I will now solve, I will make it super, super simple. Okay, it was super simple, now will be super, super. So LBM without distribution function sounds crazy, but now look at the equations. They are super simple. You have the transport equation. It can be written in this form, again with the tau here. You have the equilibrium, okay, and you have the viscosity. This is actually the equation I didn't show you before. It's a little bit about the LBM theory. Where does it come from? It's basically to compute the viscosity of the model, you take the sound speed, tau value, and you subtract 0.5. Now, this gives you some limits for tau. You cannot go with tau lower than 0.5 because then viscosity would become negative. And obviously, you cannot even approach 0.5 because getting into 0.5 means viscosity towards 0, which means basically that you go into higher and higher Reynolds numbers. So there are limits, okay, for viscosity. The tau value, the typical tau value are like 0.8 to 1.2, something like this, yeah? But how about, okay, this is how we compute the density and momentum. How about this? Let's take tau equal to 1. Just let's not say why, okay? There are some specific properties of Lattice Boltzmann when you take tau equal to 1. But now I don't discuss that. We are going from the equations, yeah? Not usual way for myself. We have an equation for the transport equation, and we put tau equal to 1. It is a value which is okay. So this basically is okay value for this viscosity. If 1 is here, this becomes 0.9, then 0.5, then this becomes kind of okay value for the viscosity. Now, let's put tau equal to 1. What happens with the equations? Then our equation becomes very simple, because now from this transport equation, if you put tau equal to 1, this basically minus this will be removed. Then we get only F equilibrium like that. Minus and minus give you plus. So then our main equation is like that. Fk, okay? Now the Fk is just transported from the equilibrium from the x. Now you think, how simple is that? You just compute the equilibrium from velocity and density and you transport. And you put it into the values in the grid. You no longer have the transport part. You don't have to scatter your function. So then our whole algorithm, and now I will not discuss much details of the equations because they are in the paper, but they are very, very simple, because you just need to compute density and the velocity from the equilibrium values that are around the given spot in the space. And then the whole solution is kept not in the values of f, because f is removed. We no longer have f here. We just compute it. We can compute f values from the density and velocity whenever we need them. We don't need to store, because they are not needed on the right-hand side. We don't have to keep the probability density function. Then we can just compute density and velocity from around surrounding grid points, okay, from the equilibrium values, which are again values of velocity, I mean functions of velocity and density, okay? So for instance, if you want to compute density, you take a sum of equilibrium distribution functions from around our grid point. And that's it. The whole solver is now here. This is the whole LBMTau1 solver. So now the whole solver algorithm looks like this. You have the complete time step of LBM algorithm. You initialize the velocities of velocities in the grid, the density, and for all directions, you compute the direction, the grid point towards which our velocity component is pointing. Okay, you compute the inverse to have the no-slip condition. And then if our node is fluid, then we basically compute the density, the velocity, and the velocity. We just take those values from the grid, okay, because they are given in the grid. We compute the equilibrium value from the neighboring node, okay, and then we put it into the equilibrium value, and then we compute the sum. And this is exactly implementation of these two, equations, because at the end we just compute the new value of density, velocity, and velocity, okay? And that's it, I mean momentum, and that's it. And then we can visualize or take the results. And the complete implementation looks like this. So then now this is the complete algorithm. It's actually something that I give you for free. And I want you to play with that. You may start with the code which is there, no problem. You can use the values which are there. You can rewrite it into your own code. You can rewrite in your own language. And this is a solution for driven cavity. It gives you the solution for the flow. Now, what to do with that, I will tell you during the labs, or I will send you instructions before if you need. But then please write an email to me, because I don't want to do this before, before we start the labs. So what we have here are the basically the velocity and the density grids. We have the obstacles, we have the x and y directions of velocity, we have all this data for the grids, and we have the top lead velocity. And we have two loops. One is the initialization of velocity and density, and then there are some boundary conditions, so for the driven cavity. And then we have LBMTau1, which basically works on two grids again and do exactly the algorithm that I showed you. And why do I show it to you and tell you that I give it for free? Because it is published. It is in the paper that I will show in a second, and you will be working with the paper. That's actually an idea, that you get the paper and you implement it, and then you can kick off from that. So you can start with that and do whatever you like. This is the solution to Poisson problem. So this is basically a channel in which you have the body force, so it is forced. You have no slip condition on top, on the bottom, and you have analytical solution to that. So you can compare analytical solution to the solution from Lattice Boltzmann, and this is tau1, in which you have the parabolic profile of velocity compared to parabolic profile of the analytical solution, and this is exactly here. Yeah, so you see it works pretty well. I also compute the error convergence, so the solution convergence. So the error is decreasing with the size of the system. The slope is -2, so there is like a quadratic scaling. Okay, so and there is Drien cavity that you will get, and this is exactly what we want to achieve. The main vortex, the second vortex, this all is the solution from Lattice Boltzmann. It can be done for even larger Reynolds number. Here is the Drien cavity for 3,200, and it is Lattice Boltzmann 1 grid from the paper. Okay, and there are some comparisons to literature. There are vortex Karman streets, three-dimensional flows, so Lattice Boltzmann 1. And there is also analysis where we show what is the memory advantage we get with Lattice Boltzmann equal to 1. And the memory advantage can be calculated from these two equations. So this is standard Lattice Boltzmann. It's a memory, so you need to twice the number of the velocity vectors plus number of the macroscopical fields multiplied by some constant value, which is basically telling which, so double of float size or so on. And this is for LBMTau1. So you get rid of 2q and you stay with twice the number of macroscopical fields times the size of the float or double. And that means you can save 76% of the memory. It's actually something that I believe is the way to go for the large porous medium. So for instance, if you wanted to compute the complete organ or something really very like macroscopic with a method like this, it will be very hard to do in standard CFD, using standard CFD tools, and it will be impossible to have the memory to keep a grid. Here, you can save even 86% in three-dimensional model. The one I chose here was exactly the one which has the largest number of the velocities I know. So the D3Q27, just to show the memory, of course, but it's like okay analysis, because this shows you exactly what you achieve. Yeah, it's like 86% of the memory. Okay, how about Reynolds number? Any ideas? You know what Reynolds number is. To increase Reynolds number, you have to do one of two things. One is to increase the speed, yeah, of the flow. The second is to change the, you remember the equation for the Reynolds number? Yeah, the viscosity, Reynolds number proportion to viscosity. How to change viscosity in tau1? That's the trick. We fixed tau. We cannot change the viscosity. So we have, I'm sorry, there is a third way to change the Reynolds, because Reynolds, yeah, is U L divided by V. Dependent what V is, you can divide by density or not. Now, you have three ways. One is viscosity. We cannot do this because we have tau equal to 1. That's an assumption. We have the velocity. We can do up to some limit because you cannot go over CFL condition, the Cauchy-Levy and so on. But anyway, you cannot go over the numerical like obstacles. So you cannot go over CFL condition. You can make the velocity, or let's say 0.1 or 2. Yeah, the Mach number has to be lower. So then than 1. So then the size of the system is the only option. And I actually had a master science thesis in which my student has done the increasing the size of the system up to the limits of the memory of the supercomputer that we used in order to achieve the highest Reynolds number. We got up to some point, but I believe that we can go even further and further. It's actually a way to work with this tau1. There is still many possibilities, but yeah, if you go higher and higher with the size of the system, you get the higher Reynolds number. So in tau1, we are basically on this line because tau is fixed. Because normal LBM lets you go higher with the tau, but the tau1 is there. Yeah, but by increasing this size, you can go and go. Yeah, it is stable. We didn't get into the unstable point. You can obviously make such things like the here is the multi-phase flow with tau1 because all the lattice Boltzmann capabilities are okay for tau1. It's still the same model. It just fixed the Reynolds number. Here is an example of the multi-phase transition, yeah, with Shenzhen. There are the very nice capabilities of this in terms of the time, but we found that the tau1 is slower. I mean, here is the execution time. It's like 1 order of magnitude slower than the usual LBM, and in multi-phase is even more. And we found it really annoying. I mean, for the paper, this was an example. Here is the implementation of LBMTau1 and LBM in multi-phase transition. So this will be tau1. Now I show you the bad things about tau1. Yeah? So it is like that because you need to compute the density around the point from the equilibrium in each point twice in multi-phase. Because in multi-phase, you compute around the point and then around another point. And this is what makes it really, you see, it's like tick, 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 tick. Here is like tick, 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 tick. You see, it's like 700. This is the normal LBM. This is tau1. It's order of magnitude difference. Okay. And there is an example of high Reynolds number flow from my student Grzegorz, who has compared lattice Boltzmann with the some source. So you see, this is actually very nice comparison of the solution of LBM in tau1 compared to the literature data. And then we also work on the tau1 implementation on GPU and on multi-threaded machines. And here we have an example of the speed up of lattice Boltzmann tau1, which is much more capable of speeding up on parallel machines than usual lattice Boltzmann. But I will not go into details. The paper is in the review. Now, to summarize, the LBMTau1 is a very simple algorithm with shorter implementation than usual LBM because just you have 2 lines of code, really. Accuracy is the same as in the lattice Boltzmann BGK. BGK means Bratanger-Gross-Krog approximation of this collision term. There are possible extensions towards different things like in usual LBM. It is potentially very attractive for low Reynolds numbers and for large systems. I think it's good for teaching. That's the reason why I keep it here on the. And the minuses, it has this all these drawbacks and advantages of fixing tau. You need large systems for large Reynolds number. For single phase, it's 3 times slower. For multi-phase, almost 10 times. Not necessarily is good for GPU. There is some problems. On the website, on my YouTube channel, you can find the whole example of tau1 and LBM in the way that it is like useful for the YouTube videos. Sorry, I'm now after 1 hour of talking, I cannot find my words. But this is like complete introduction in a way like tutorial. Yeah, it's 5 minutes tutorial of how to work with that. I explained from the paper all the terms in the algorithm. I spent a lot of time on this video, so you can really use it. And also there is a paper which you can find useful, and this is actually what I want you to start with during your labs, because the paper The whole paper is actually the whole talk I gave you about today with more details. And this is the paper which shows the LBMTau1 in two different variants with all the details and the whole implementation. So you have the results of this cavity, you have some kind of analysis of the model, and you have the full implementation in the appendix, which is basically your task to do. Okay? Okay, and now to end the talk, I also recommend you the book, which is in the library, that you can find the whole chapter about LBM and about LBMTau1. This is actually, I spent a lot of time on writing this. These are a lot more details and a lot more things that I could cover here, but we have limited time. So you are welcome, and it is available for free in our library, so don't worry, you don't have to buy it. And then at the very end, we deserve a cup of coffee, and let's finish at this, our last slide and last lecture on CFD.